a dar inicio a la segunda jornada de trabajo acá en WEA. Mi nombre es Juan Carlos Figueroa, soy el chair de esta charla plenaria que va a ser impartida por el profesor Roman Neruda del Instituto de Computer Science de la Academia de Ciencias de la República Checa. Hola, Roman. Hola.
Hello.
Roman Neruda trabaja con el Instituto de Computer Science de la Academia de Ciencias de la República Checa en el departamento de Machine Learning, donde se dedica a trabajar en ciencias de la computación, algoritmos evolutivos, auto machine learning y meta learning. Él se graduó de la Facultad de Matemáticas y Física de la Universidad de Charles y obtuvo su PhD, su doctorado, del Instituto de Computer Science de la Academia de Ciencias de la República Checa. Entre el 95 y el 96, él estuvo trabajando en el Laboratorio de los Álamos, muy famoso a nivel mundial, en proyectos en conjunto con colegas del Carnegie Mellon, de la Universidad Koblenz y de la Universidad de California en Chico. Y también de la Universidad de Saint-Étienne. Él es coautor y autor de más de 100 trabajos internacionales ya publicados, ¿cierto? En The Web of Science, él tiene 116 publicaciones, más de 250 citaciones, tiene un H-index de 8, y en Google Scholar tiene 225 publicaciones, más de 1.300 citas, y un H-index de 15. Él enseña actualmente algoritmos evolutivos y sistemas multiagente en la Facultad de Matemáticas y Física de la Universidad de Charles. Recientemente se ha unido a un nuevo grupo que se llama el Centro de Modelado de Procesos Sociales y Biológicos, BISOP.eu, donde está trabajando en modelos multiagente para simulaciones epidemiológicas. Pues claro, ahora estamos con aquello del COVID. Dobrý den, Roman. Vítejte na naší konferenci. Děkujeme, že jste přijali naše pozvání. Welcome to our conference, Roman. Not so bad, right?
It was perfect. Thank you very much, Juan Carlos. Thanks a lot for introducing me. And I would like to add that Universidad Distrital in Bogota is, and your team is one of my most precious places and people I like to collaborate with. And I am really honored to be invited to present the talk today. So I'll close my camera as well. Just leave the screen sharing with the slides, and I will start if Juan Carlos agrees. Perfect. So as Juan Carlos said, one of my areas of research and teaching is multi-agent systems. I'm also doing lots of machine learning, but this talk will be more about agent-based models and multi-agent systems. And it's actually a nice history. And let me go. The interesting thing is that when the pandemic started, like a year and a half ago, we, with a group of people from different organizations in Czech, the Academy of Sciences, different institutes, Charles University, other universities, we sort of started this group first as a discussion and then as a modeling group. And it was really sort of guerrilla style because it was a severe lockdown, so we had phone calls, Zoom sessions pretty much every day at the beginning. And we started to develop some epidemiological models. And there were people like medical doctors, people from sociology, doing surveys about human behavior, psychologists, statisticians, computer scientists. And so what I will be presenting today is sort of a group work with more than a dozen of colleagues from different institutes. And for me, it was a very unique experience. I mean, the pandemics obviously still affects all of us. But this was like a unique experience to start a work with a different group of people and in this sort of very intense way. I hope that you will find some of our work interesting, and what I will be talking about today is how do we actually model epidemic? What are the traditional models of epidemic? And because I would like to talk mostly about agents, like software agents and agent-based models, I would like to show you why the agent-based models are useful in sort of detailed modeling. We will be also talking about social networks, networks of contacts. Sometimes in literature, this type of model is referred to as network model. So we will see that the networks, meaning graphs of contacts of people, are really a key point for successful modeling of epidemic. And then I'll show you some case studies, what the model we have developed can actually do. So I'll show you the model of a municipality in Czech and the model of a grammar school. So that's the outlines for the talk, and let's move in. The traditional way how to model epidemic is actually more than 100 years old. And it's sort of interesting that the basic principles are still there. So how do you model epidemics? Well, basically, during epidemics, you can think of the people that are still not having the disease, right? Sort of healthy people. And then people who are currently infectious, who got the disease, and then people who are after the infection. So that's really a traditional approach where you say, okay, so we have these three groups of people. The healthy people are called susceptible, meaning they can get the disease. The people who are currently ill are infectious, right? And the people who recovered are called recovered. This group is called recovered or removed, because of course, depending on the disease and severeness of your individual case, you can either survive or die, right? So the traditional model is called SIR because we have these three groups of people: susceptible, infectious, and removed. And of course, it's a state. You can think of it as a state-based model where an individual can go from susceptible to infectious, getting the disease, right? And you have some coefficient that tells you what is your probability to become infectious. And then when you're infectious, you have again some rate of recovery that tells you how you move from the infectious state to the recovered state. Nowadays, when the COVID epidemics is here for some time with us, we are also considering that maybe you're not removed forever because you can get the disease again. So some kind of immunity that you received can fade out and you can get back to the susceptible state. But if you look at this traditional SIR model, you can actually solve it by describing it with simple differential equations. And so we have the susceptible, infectious, and removed or recovered, the optimistic scenario. We will not consider the fading immunity for now, because this is sort of the very traditional 100 years old formulation. And what you see is that people actually moving from S to I, right? And how do they move? Well, the rate, how you move from S to I depends on your contacts, which means you're having contacts by the number of people in I and number of people in S, and divided by
Recording in progress.
What happens with the infectious people? Well, with the infectious people, some people are coming from the susceptible group, right? So that this is the same part, except this was negative and this is positive. The infectious people are growing, and then some people are recovering. And again, the recovering rate, because we're talking about differential equation, is number of people in the infectious state times some gamma recovery rate coefficient, right? And yeah, so the recovered people is this term, right? The people who have actually recovered. So it's sort of simple, right? Everybody understands it. The population is moving between susceptible, infectious, and recovering, and you have sort of simple set of equations that describe it, and you have two perimeters, basically the beta and the gamma, that tells you what's the speed of the transitions between S and I, and what's the speed of transition between I and R. So as I've said, the beta is basically a product of number of actual contacts that you achieve for some period. Usually it's days, the days are ticking, and the infection probability. And the gamma is the recovery rate. These two are actually important, and sometimes we talk about the R0 coefficient that basically describes the illness, the infection, as beta over gamma. And this is called basic reproduction number. And it tells you how infectious the disease actually is, right? So different infectious diseases have different R0. So that's one thing to consider. And then this is a property of the disease, and you can still reduce your chance of being infected by reducing your contacts, right? So that's also pretty straightforward. The interesting thing, if you model the disease, is to actually consider inverses of those gamma and beta, because they give you time in days. So 1 over gamma, if you have gamma is a sort of recovery rate, so 1 over gamma is actually some average time in days, how many days you spend in the infectious state. And the beta, 1 over beta, is some sort of average time between you can get the disease, right? Between your contacts, infectious contacts. So the R0 is the property of the disease. During the epidemics now, usually people try to estimate the current speed of the infection, and the current speed of infection, referred to as R without the 0, is basically the R0 multiplied by the contacts, the number of actual contacts. So it's just a speed of the infection, but it's one of the numbers that's really followed, especially here in Europe. I don't know how the situation is in South America, for example, but we see the estimate of R every day in the news. And if R is bigger than 1, it means the epidemic is growing. If R is smaller than 1, it means we are exponentially decaying, right? Usually the way how you estimate the R is that you go 2 weeks in a history and you consider some week averages. And so it's not really an exact number, it's really an estimate of the speed of the epidemics. So we were kind of lucky in Czech during the summer. We had the values below 1 and the daily infectious very low, like 100, 200 people. And nowadays we're getting R, the actual current R being like 1.3. So everybody is expecting that we're sort of having another wave of the disease. So this is just to give you an idea about the basic traditional model, and so we can actually solve this set of simple equations and solve it analytically. But these numbers, the beta and the gamma, and especially the contacts, it's not easy to guess, right? So that's why we are trying to make more complex models. And one of the complexities we can add is to actually create more states. So you remember we had S, I, and R, right? And now we try to add more states to describe the disease in more detail. So first of all, what's interesting is that we have R like really recovered, and we have D state for the deceased people who actually died out of the disease. Instead of S, we can also have the false symptoms, like having just a common flu. So that's a false symptomatic case, and we make more details in this section, which I will now describe. So first of all, the dynamics of the disease is that when you get infected, you're not infectious at once, immediately, but you have a few days where you are the so-called exposed. You already have a virus, but you're not infectious yet. So that's why we have the state E here that says exposed. And also this red arrow is the only way how you can actually get the disease as an individual, right? So you go to exposed state first, and then you're going to infectious states. For the infectious states, we have also created more detailed sequence of states, and these deal with the way how you exhibit symptoms. There's some people are symptomatic, meaning they can tell they got the disease by symptoms. Some people are asymptomatic. They do not have any symptoms or have just mild symptoms. So that's why we have this asymptomatic way and the symptomatic way of going through the disease. And so we have infectious but without symptoms, infectious with symptoms. So you can have some small period of time where you're infectious, no symptoms yet, then symptoms. And then we have a states J that say, well, you're not infectious anymore, but you still can have symptoms or not known symptoms, but you still have the virus in you, but you're not practically infectious. So this is how to describe that we have this extended model. And also you see that we have sort of a mirror of states here, with upper index D, and these are actually detected people. So for each of the states of the disease, we have its mirror that says detected. Detected meaning that they got tested and they are actually caught by the statistics, right? Because if you think of it, they say that, for example, in Europe, in Central Europe here, probably 2/3, 1/2 or 2/3 of people go through the disease without being traced, tested, and without probably knowing that they got the disease. So that's why we have the detected states here, because the numbers that are reported by authorities are actually of those detected states, right? You're still not catching many people who get the disease and go through it undetected. So from the basic SIR model, we got into a model where we have more states for symptomatic and asymptomatic disease, and we have more states that actually can model how the authorities are handling the disease, how efficient the detection is through testing and contact tracing and so on. So this is the extended model we're using. And one more thing that we can add to the basic model is the statistical properties of the times you are spending in those states. So I've said that we have the beta, and 1/beta means that you stay in the susceptible state for a couple of days. 1/gamma tells you that on average you stay in the infectious state for a couple of days. But this leads to exponential statistical curves, and they are not actually good for detailed description, because we know that the density of the statistical distribution that describes how many days will you stay in some state is not really exponential. So that's why I'm showing you these curves. The one is statistically measured, and it's a thing called RNA positivity. So you can measure it clinically by tests. And on the x-axis, we have days. So when you got the disease, this is the number of days you stay RNA positive, right? And from these and from other surveys, we can get those distributions of days, how many days you're spending in the E state, the incubation. So you can see that the incubation, typically you stay around 5 days. So 4, 3 is still a lot cases. More than 10 is very seldom, right? And the same thing we can get for other states, pre-symptomatic and infectious states, and it's again number of days you're staying. So if you simulate the model, you can actually get more detailed simulation, because when you know these curves, you can actually for each individual going through the disease, you can generate number from this statistical distribution telling you stay in the infectious states for 4 days, for example, right? So it's a more detailed description of how you go through the states of the disease. And also, if you do the agent model, you can actually do this individually for every agent, meaning every individual. I will tell something about this in a moment. So why the agent-based modeling? Well, the agents in computer science, they are usually software entities that are to some degree autonomous or intelligent and adaptive. From the point of view in agent-based models, they represent some simple but sort of detailed components of a system that creates a computer model. The agent-based models are actually quite popular in many application areas, from physics, where you can think of the agents being particles, for example, to biology, where the agents can be animals in an ecosystem. In economics, agent-based models are very popular, where you can model different behavior of people by different types of agents and their interactions, right? So usually the agents have some kind of memory. A useful abstraction is agents with states, like a state-based machine. Think of finite automata with stochastic ways to go from one state to another. And so this fits perfectly. Now you can think that an agent is an individual. The states for us will be the states of the disease we have just described, right? And so we can, the agents have to interact somehow, right? For the interactions in multi-agent systems or agent-based models, we have the so-called environment, which is like the virtual place where the agents exist. And the environments can be, again, very diverse. So you can think of a 2D or 3D physical-based environments, like for physics, for example, this can be a 3D model of something, of a space. In biology or economics, it can be like a 2D model of a city, where you model the growth of the city and so on. For epidemiological models, the natural way how to represent the environment is actually graphs. Graphs where the nodes of the graph are the agents representing the individuals, and the edges of the graph are contacts of the individuals. So this probably requires a bit of comment. It would be actually cool if you can do epidemiological model that looks more like SimCity or some computer game where you actually have people going on the streets and everything, but it's just too expensive, right? So the abstract solution where you have the graph, a network that actually represents the contexts, and you operate with the context of the people, is sort of a cheaper yet can be very detailed solution to this. So we're not, in our model, it's not like a cool animated SimCity type of model. The individuals have connections represented by the edges of the graph. For a detailed model of context, we need basically a multigraph where each individual can have several connections to other people related to different activities. So one activity can be context within a family. Another type of context is context with your colleagues at work or at school. More random context that when you go to a restaurant or shopping, use public transport and so on. So these are types of contexts that we can represent in our network or graph that is actually a multigraph. So this type of models is called a network models from sociology. And I will now describe how we built our model. So the important thing is to actually get some detailed knowledge about the contexts of the people. And there are already some research about how often people meet other people. Like this is a research by Prem and colleagues that provides model of number of contacts of people depending on their age. So here it's represented as a sort of a matrix of contacts where you have age groups on each axis, and this tells you how many contacts relatively this group has. So for example, you can see that the diagonal is very dark, meaning that we tend to have many contacts with people of similar age, right? So that's sort of interesting. Of course, the social active people are like from 20 to 50, 60. These are the most social active people, the darkest area here. But you can also see some contacts, some darker area that goes through one generation. So this would typically be like a parents with the kids, right here, some grandparents with the kids, right? So grandparents with grandkids here, grandparents with the parents of the kids, and so on. So this is sort of a static view and quite general, how many contacts you have depending on your age. And that's one of the important inputs for our model. Another important input that we use is how many contacts relatively you have depending on the type of context. So now I take a look at the left column, and this tells of all your contacts, which can be 10 people a day or 50 people a day, doesn't matter, how many contacts you have of different types. This is again a result of sociological surveys, and it's really an important thing. So it tells you that more than 1/3 of your contacts is within a family, right? Then you have school contacts, work contacts, the restaurants and visits, quite a lot, shopping, not that much, outdoor contacts, very low, some services, and then you sort of have other, right? So this is just to show that we can have relative strength of contacts depending on the category. The second column is something that's not generally known, but for the context, you remember even from the very basic model, you have to have the infectious rate, and the different type of contact can have a different infectious ratio or probability of getting infected. So for example, so this actually tells you the relative chance to be infected depending on the type of the contact. So for example, the family, it's very intense. The contacts in a family are very intense. You usually live with the people in their household. So the relative chance you're getting the disease from your closest people in a family is big, because you're spending lots of time with them in close environment and so on. So these numbers that are represented here are actually an estimate by experts, by medical doctors and so on. So the relative frequency of contacts is more like a sociological research and more reliable numbers. This is estimate. It's not estimate by one medical doctor. It's being done through some surveys and so on, but still it's an estimate. So for example, for the outdoor, you see we have the outdoor activities here. We have almost zero, very low probability to get infected just outdoors, right? So that's So that's another important input that we need. But so far, we were talking about static numbers, right? Like how many contacts you have, how can you divide the contacts between different types. But what is important during the epidemics, you're not behaving constantly. So this is an example. We were lucky in Czech because when our team started, there was a company that's doing sociological surveys, and they immediately started to survey the people about the context they're having during the epidemics. So this, what you can see, is sort of a calendar, how the relative frequency of contacts of people was evolving during the first year of the epidemics. So you will see that in Czech, in the mid-March, there was a very strict lockdown, lasted for like 2 weeks. It was very strict. Then there was some kind of opening of things again, and then we had the second wave in the fall, and before Christmas they sort of opened pretty much everything, and then we have another figure where we have another wave here in the spring again, and then very quiet summer. So this actually tells you that people were restricting their contacts a lot, right? So even the contacts within a family were quite low during the lockdowns, and all the other contacts like shopping and so on was like at one point practically zero, because most of the shops were closed, for example. So the dynamics of the contacts is very important, and it's also one of the inputs for the model, right? Because you have to know how many contacts people have every day, and then you can simulate the disease spread in the society, right? So this is one of the important things, and we were lucky that in Czech we had quite a detailed survey that started immediately at the beginning of the epidemics, and that actually still runs. And so we have every 2 weeks we have contacts. So this is the survey from the website of our colleague who's doing these, and so this is partially in Czech, but you can see that that it's even divided into age groups. So these are different age groups. So we can actually have detailed numbers for people, for younger people, for mid-age, and older people. And you can see that their contacts are quite different, especially for the seniors, right? So that's some of the inputs we have to consider for our model. And now I will be talking about the actual model, the how we model the municipality. And so we have chosen an area in Czech. It's sort of a county, as we call it. So it's an area where we have some 56,000 inhabitants, and it consists of a county town, the center of the area, and a couple of villages around. So you see this on the left, the sort of animated thing that's actually a result of one of our simulations of the infectious spread. And so what you actually see is sort of an actual map of the area with the main town here and the villages here. We had to choose some area that doesn't have that many contacts with the neighboring areas. So first of all, the choice of the area, it's called travel to work area, meaning that most of the people from those villages, they actually travel, they either work here or travel to the county town for work. We have some export and import nodes, but mostly we were looking for some area that is not close to some big city, say Prague or something, because then everybody would go from here to Prague, right? And we needed some sort of homogeneous area where people do not travel that much during their usual life, during weekdays, for example. So, okay, so we have 56,000 inhabitants. There's like half of them in this town and another half spread it around in the villages. And for those almost 60,000 inhabitants, we actually have something like 3 million contacts. So the contacts are divided into the layers depending on the type, and the sort of larger groups of contacts refer to the family, school, work, shops, pubs, clubs, and so on, and transportation. So these are the layers and groups of layers reflecting these activities. And so the number of inhabitants that are the agents in the individuals, right, is not that big. We're having 60,000, but the number of contacts is quite big. So having 3 million contacts, that's quite a lot. So for example, when we were thinking of creating a model of some bigger city like Prague, this would be actually difficult, first of all, to get all the detailed information. And second, the number of contacts would be big. So still possible, but the number of contacts is actually the problem, not the number of inhabitants. So for when we started to generate the agents, you see that they are located geographically, right? The graph, you see the nodes of the graph. So they have the place where they live, right? So the model is really detailed in a way that it mimics the situation in that particular municipality. So we know how many people live where. We know where the schools are, the hospitals, the shops, and so on. So we generate the population depending on the type of the population and ages and everything. So it corresponds to the current state statistically, right? It's an artificial population, but still it has to have the same statistic measures like number of young people, number of old people, and so on. We put them into houses because we know how many people live on the addresses there and so on. So the model of the individuals is actually quite detailed, and it reflects the reality, although it's an artificial, statistically generated population. And the contacts, again, we generate based on the position of the schools and shops and so on and so on. And transportation as well. So we know how the public transport is generated here, and so we try to reflect the real situation. The important thing about the agent-based models is that we really, if you take a sort of microscopic look at one particular node, one particular agent, this is a node number 29,691, and so we were looking how these agent actually, what are the properties. And I was because one of the colleagues who's actually programming with us is my master's student, nowadays a PhD student, and she's called Gabriela. So we identify a node that somehow corresponds to her statistical attributes, and we found out that there's a node 29691, and we call it Gabriela, and so it's a female, 19 years old, a student. We have an address, so this actually, you can put it into a Google map and see where it is. Number of contacts we were checking. So young people are usually quite socially active, right? So she's got the total number of possible contacts is more than 200, and they're like school contacts, family contacts, some shopping, restaurants, going to a club, using public transportation, and so on. So the node in the graph, we can actually explore, and we see that it has a concrete data, right? And based on this, we can actually set more data, not like the contacts, but also, for example, the perimeters of the disease that are age-related, for example, right? So then I will show you some examples how we model this during for the epidemics in Czech Republic. So first of all, it's not a straightforward to put all these numbers into a model and then run the simulation. Even though you have the perimeters you think that are correct, like from the medical doctors about the infectiousness and so on, still, if you run the model, you usually don't get the right numbers straight away from the model. So one of the problem is what data can you actually use to fit the model? And so these are these are the number of detected people, right? So I'll try to go back. So remember the states of the agents, right? And so these are the undetected people who go through the disease, and these are the detected people. And so you can get detected by being tested positive, right? So this can be because you go tested because you don't feel well, or because there's some contact tracing policy in charge, and so somebody gets the disease, and so the public health officials call you and ask you for your contacts in the last 5 or 7 days, and you say, okay, I met these guys and so on, and so they force you to go to testing, right? So this is how you get detected, but the detected numbers are lower, definitely lower than the numbers of actual ill people at the time. And as I've said, some people speculate it's half of the people, some people say only 1/3 of the people is detected. So we don't know, but these numbers are only numbers we have, right? People that get tested positively, people that get to the hospital, and people that die, actually. So these are the numbers, and so the fit of the model is actually quite a long procedure where you start with reasonable values for all the perimeters, and then use trying to adjust them a bit by some optimization. So we use different things, from the very simple grid searches to colleagues are using Bayesian approach. We also used some evolutionary type of optimization to fine-tune the perimeters to actually fit the model. Once you fit the model, you can start doing some artificial computational experiments. So this is just to show you couple of these experiments and what they say. What you see here is 4 possible scenarios for the epidemics, and this blue one is actually what actually happened, right? So this is how we fitted the model. So we have detected infections in our municipality, so the numbers are not that big, because we're having, you remember, we're having 60,000 municipality out of 10 million Czech Republic, right? So that's what happened. This is the epidemics, the first wave of epidemics, and there was a very strict lockdown, and then the epidemics sort of went down. And so we were trying to see what would have happened if the individuals, the people, would have not changed their behavior, meaning wearing masks, like protecting themselves. So that was one thing. People changed their behavior a lot. And another thing was there was a lockdown in many contact layers. So the shops, except the groceries, were closed most of the time. The restaurants were closed, and so on and so on. The schools were closed. So this is the real thing that happened. And now we were simulating, for example, what if the government imposes the lockdown, but the individuals are not cooperating, they're not changing their behavior. So this actually shows that it is necessary to handle the epidemics. It is necessary that people change the behavior. So it would take longer, but then the epidemics would go sky high without changing people behavior. And then without some closures of the parts of the society, this is the orange curve, no contact restrictions, this would skyrocket even earlier. And of course, no measures at all would also mean like a sort of a disaster. Well, now people have different opinions about what's the better policy, how to handle the epidemics. But it's interesting to see that actually both some government imposed measures and that some change of human behavior, individual behavior, is necessary to handle the epidemics easily. So I'll skip this one, but I'll show you that's an interesting study. When the vaccines came, it was basically the beginning of this year. People were discussing if it's better to have a long interval between the second dose or a short interval. So we were running the simulations with the long and short interval vaccinations, and we have come to these findings. What we actually tested was the 2 cases that were actually used in Czech Republic. So first, they said that the interval between 2 doses would be 6 weeks, 42 days. And now they shorten it because now they have enough vaccines. They shortened it to 3 weeks, 21 days. So from our comparison, it actually, what are you trying to optimize, right? So probably number of severe cases and deaths, right? So we actually found out that at the beginning, it would be better to do the shorter periods, right? And in the end, it's better to do the longer periods. So that's actually the opposite that happened, right? From some logistic reasons and so on. We have published this. I have a couple of preprints available for the results I'm reporting. So we now have a preprint of this study on medRxiv. So that was kind of interesting that we can actually simulate the various properties of vaccinations as well. Another case study we did, which is also some kind of interesting, is how important is the contact tracing? Because in Czech, it was a big issue that the officials, the public health system, was criticized that they were not able to actually do the full contact tracing, and they didn't have capacities. Well, it's sort of difficult, right? Nobody expected the pandemics. So what we were trying to simulate here is we said, okay, so let's see how different tracings in different contact layers are important. So we say, okay, so we will have 4 contact categories: the closest people, the family, then your work at school colleagues, and then some leisure, and then other layers like public transports and so on and so on. And we tested 4 scenarios that actually were able to find all your contacts within the family, or all your work and school contacts, and so on and so on, right? So by 1, 0, 0, 0, it means we're tracing in family only, but we're efficient in finding possible contacts in family, which usually is the simplest way, right? We all remember our wives and husbands and kids, right? The 111 would mean ideal tracing. We can catch all the contacts, even from public transportation and so on, which is really unrealistic, right? This can be achieved to some degree with some application in your mobile or some electronic devices for actually following you and catching the contacts. So we were again running the simulations where all those scenarios for no contact tracing at all, only family, family and work and school, family, work and school and leisure, and ideal tracing, right? And you can see that different scenarios lead to sort of expectable results that we can expect from this. And what we have found out is that in general, if you have a lockdown, at least with some layers, it's usually more effective than any type of tracing. This is kind of understandable. If you close the restaurants, for example, they're closed, there's no contacts, and so this type of measures is effective, although obviously not really popular, right? If you have those like rather strict contact restrictions, either imposed by the government, or maybe you are careful and cautious and not having too many contacts, then the differences between the contact tracing strategies are small. So of course, with relaxed contact restrictions, the effectiveness of these contact tracing strategies is different, and it's substantial. So if you have no lockdowns and restrictions, you should have good contact tracing, basically. And this, I think, is one of the results that will be that will be applicable to the current situation here, because we're getting higher numbers of infected people, but the government is not really does not expect to do any lockdowns anymore, because of course even if you're a good government, you still have to consider the cost of economy when you're closing it down, right, in some sectors. So the message from the government now is no restrictions, no closing businesses, and so on and so on. So it tells you that actually a good contact tracing is important in that case to control the epidemics. And I would like to show you the super spreader event. So this is also one of the realistic cases that we saw. So consider like a soccer match or a rock concert, some event where you have hundreds, thousands of people, and they can serve as the so-called super spreader events where you all of a sudden have big concentration of people. They can get infected and spread the infection to their families and work and so on and so on. So we were studying the efficiency of those contact tracing strategies in this case, and what we have found is that the super spreader events are so extreme that it pays off to try to have some really good contact tracing. So for example, imagine that you go to a rock concert and they force you to open some application that actually records your movements and so on. So that's the ideal contact tracing we can think of, and that's really important for those to prevent those super spreader events. Although we don't think that this is practically realizable, but that's one of the outcomes of the simulations. And the important thing, the important detail, I would like to. Oh, I'm sorry. I should speak a little slower. Is it getting better? Because I'm getting more tired. So I hope it's getting better. The important thing I would like to show you is when we were talking about the Gabriella, the one individual, we can actually follow her during some scenario and see what happens to her. So this is an example of 3 of simulations with the super spreader party. And important thing that I haven't probably said before is that all those simulations that you see are not one simulation, but usually we run the simulation at least 1,000 times and then compute the statistics. And then we compare the relative results of those statistically enumerated 1,000 scenarios. So the simulation have a higher variance of different results. So we really, when we simulate, one run is not enough. So we have to do more runs. And this is actually nicely illustrated here for the 3 different scenarios, what happens to Gabriella when she goes to a party. So the one scenario is that the Gabriella goes to the party, gets the disease without any symptoms, without noticing. And so these are the days. So that's the day of the party. So she gets infected, doesn't notice, is infectious, but no symptoms, and then changing to recovered. She's young, very low chance for severe symptoms. So this is one scenario. She went to the party, got the COVID and recovered. Nobody noticed. She was not detected, right? Another scenario here is that again got the disease, was symptomatic, slowly going to asymptomatic state, then symptomatic state. She got detected and stayed in a quarantine. So that's another scenario. Another scenario is here. It's again one of the scenarios where she got the disease. There's like hundreds of scenarios where she did not, but these are not that interesting. This is interesting because she got the disease, started to feel some symptoms, did not feel well, so stays at home. Somebody reported her as a contact, and so she was quarantined again and stayed home, depending on a policy, for another, I think it's 2 weeks now, right? So these are 3 different cases from one type of the simulation, what can happen to this one individual that we call Gabriela. So this is one type of result. In the last 5 minutes, I'll show you another type of simulation. We've used pretty much the same engine, the same simulation engine, but with different graph, different individuals, and different network of contexts. And this is a research we were doing for the Ministry of Education, because they asked us, what should they do in schools? Like, what's the efficient way? Because the schools were closed first during the lockdown, and then they wanted to reopen it, but they were asking, should we test the pupil, the students? Should we, alternate 1 week going, 1 week not going? Is it better if half of the people go to the school and half of the people stays home? Is it better if you cut the classes in half? So what's the relative efficiency of those possible measures? And they actually prepared, with the cooperation of our sociological colleagues, they prepared a survey where each of the teachers and students, they filled out a form to get information about how many contacts they actually have. So we ended up having a nice detailed model of a school where we have 600 students and some 50, 60 teachers. We have many types of contexts. Now these contexts are, because we're studying only the school itself, right? Context in class. So you have some, you have all your classmates, some kind of context, but some of the classmates are your friends, right? So you have more intense contexts with those. You have context out of the class, context when you're walking around the building, corridors, cafeteria, teachers' offices, and so on and so on. And what we were studying here, as I've said, was the partial closures, weekly alternations, and testing, the effect of testing. So this is how the social network looks like. You can actually create a picture. These are the teachers. These are the students. So you can see the big clusters corresponding to the classes, actual classes, right? But it's not all the context there. So this is how the graph look like, and I will show you some results. Again, you see we have tested many types of weekly alternations, like younger kids, older kids, half of the classes, not depending on the age, and so on and so on. And so the findings are actually interesting, that if you do the alternations, meaning for each class, you say you go to school for 1 week, and you stay at home for 1 week. So this actually is enough to reduce the chance of COVID spread by 75%. And that's actually, I mean, surprising that this alternation is really efficient. And if you combine it with testing, even if the test is not very efficient, I will not go into detail, but we have antigen and PCR tests. The PCR are much better in terms of their sensitivity. But even if you have a test that's not really that good practically, so using like weekly tests reduce the infections by other 50%. So that's actually really good. The alternations and some testing doesn't have to be ideal, is enough to suppress the infection quite a lot. We have, during the simulations, when we were studying the agents, so we were curious what's the role of the teachers. And we have actually found out that the teachers quite often acted as some kind of bridges, because especially for the older classes, the teachers go from class to class. So they sort of connect the clusters by the contacts. And so they were responsible for more infections than is their number in the school. So it also tells you that to protect the teachers is important, right? Not only from the points that if you have teachers with the disease, nobody can actually teach, but also from the point of view that they are the ones who connect the clusters of different classes. So this was another study, and that's pretty much it. I will try to conclude. So what we have actually done, we have created this software that uses all the principles I've just described. It's actually available on GitHub, and so it connects all those components. It's programmed in Python, and it's quite efficient actually, although it's Python, because it uses some optimized libraries. And so it's called Model M, and it's quite a versatile tool. There are some other software simulators like that in the world, but I think that there's like a 5 or 10 that are really good, and we hope to be one of them. And the final thing, as I've said, we started this type of research as sort of a group people that started to connect at the beginning of the pandemics, and now you see my colleagues. I reported the work that they were also working on, and you see that there's people from Academy, Charles University, other universities, and so if it were not for them, these results would not exist, and I would not spend interesting times with them actually. So that's it for my presentation. Thanks again, and I'm ready to questions, comments.
Moc děkujeme, Roman, for your presentation. Yeah, I know my Czech sucks sometimes, but
Muchas gracias. Muchas gracias.
Tenemos preguntas del público. Yo puedo ayudarles si necesitan un poquito en la traducción o lo que sea. Pueden hablar en español, creo que pueden activar su micrófono y yo les ayudo con la traducción o si quieren directamente preguntarle a Roman.
May I speak?
Yeah. We hear you.
Yeah.
Yeah, I just have a question for Roman and something a little bit basic about the assessment of data related to COVID. I want to ask about the timeline of the data that was requested and analyzed. How much time did it take to do such a thing, and why the computational analysis was used?
Yeah. So, well, you have different types of data, right? Some data are about the daily cases, like detected cases and cases of people died of COVID that day. And so what we do know, these are published by local authorities, and we just have to believe them. So those statistical data that are published by Czech health authorities about the severeness of the disease, we just have to believe them. We don't have, what can you do, right? So of course there are some options if people dead because of the COVID are really and so on, but it's really difficult. So that's data, we don't know what to do with them. The data about and
Por favor, desactivamos el micrófono.
Es el papá, por eso la gata los dejó aquí.
Ruido.
Ese es un gato, pensó que era una gata.
Okay. So I will continue the answer. I hope it's okay.
Yeah, please.
And the other types of data about the social context and mobility, we are trying to verify. So we have one source, that's the sociological surveys, but we can actually verify with data from Google Mobility and Facebook Mobility. And that's what actually we are doing. So we are combining different data about the mobility and checking if they sort of correspond. So we have statistical analysis of the data and checks if they are reliable, I would say, right? And other types of data are the results of our experiments. And as I've said, here we can only do to repeat the experiments like many times and see if they're statistically correct, if they fit the official health authorities data, what we have. Still, I can understand that there can be some doubts about the data, because, for example, nobody really knows how many infections you really have, right? So that's one of the things that we don't really know how to verify. So the doctors say that can be anything between 2 times more to 3 or 4 times more than detected, and so we check if our simulation numbers correspond to that. If we have better estimates for some of those perimeters, then probably the model can be better.
Thank you a lot.
Any other question or comment or nope?
Maybe I have one last comment, because this question was actually pretty good, and but just one last thing. This model is really detailed, And so with that many parameters, we cannot be sure that it's, correct. And so that's why we are trying to say things mostly about the relative results within our model. So we are not, trying to predict the epidemics as it is and predict some absolute numbers and saying these are correct. But what we can say, I think, even if the model is not that right, is that the relative efficiency of different measures makes sense to compare them, right? So our aspiration is not to have like a forecast that fits exactly number of cases, but it's more like about what a lockdown in one area, what a lockdown of schools or restaurants mean. And we can say it means reducing the epidemics 50%. Yeah. Thank you.
All right, that's a good answer, because sometimes people want to get a good forecast to make a decision a day before.
Yeah.
But in this kind of situation, it's pretty hard to get good forecasts, right?
Yeah.
Almost
Yeah.
impossible, in my opinion. But
yeah.
I have a question. But before that, Claudia says, congratulations for your work in Spanish. But
Yeah.
Claudia is saying that.
Gracias, Claudia.
And
no, a ti, muchas gracias.
De nada.
Sergio, a good friend of the house, of our home. He wants to ask you something. Please come in.
Thank you, Juan Carlos. And thank you, Roman, for such a fantastic talk. It seems you have invested a lot of time doing this model. It looks very, very nice, interesting findings, very detailed, as you mentioned. So congratulations to you and all of your team. I actually have two questions. The first one is, we have done some work also modeling with agent-based simulations on the dynamics of the epidemics. And we were wondering if we can use these models. I mean, most of these models have been based on the modeling the behavior of epidemic variables, right?
Mm-hmm.
But we see that in society, other variables are also important. I mean, economic variables, mental health variables, educational impact variables.
Yeah.
Do you think it will be possible to use, for example, using your model, it is possible to make an adaptation to study the behavior of these other variables, not the epidemic ones?
Yeah.
And does it make sense, for example, to have like a totally or entirely simulation of all of these aspects of the society?
Mm-hmm. Yeah, for example, with the economics aspects, we were actually considering this, but and I think that technically it's possible to say, to have some kind of cost function if the agent changes behavior, does not go to work or something. So you're starting computing from the simulation the financial loss, for example, right? So this, but we were not actually able to get the economists to get us good, like some kind of estimate what should we put there, right? So I think technically it's possible to because we're counting many things during the simulation, right? So from the programming point of view, from the simulation point of view, it's possible to just put more properties there and just count them. The problem we encountered when we were talking to people about the economical aspects, for example, that they say that they're not sure how what the numbers are, right? What to say about the numbers. I can imagine that you can start with some estimates and maybe a smaller thing, you know, not like all the money, but maybe like losses of the businesses, for example. That should be easier, right? Yeah. So yeah, in principle, it's possible.
Thank you. and I got another question, if you don't mind. I was wondering about the runtime of the simulations. You mentioned that you repeated the experiments about 1,000 times. How long did it take to run that such a big amount of experiments?
What it depends, but for example, the school, it's fast. So like to simulate the school for, I don't know, 150 days, one run is a minute or 2 minutes, so it's okay. For the town, it can be like 30 minutes or 1 hour, one run. So that's why we actually have the system. We run it on a cluster with many processors. So that was actually the technical part to make it run in parallel and to share the data. And so what we usually do is we run it on a computer that has 100 processors or cores. And so even if it's 1 hour for one simulation, and we need like so we run it 100 times. So overnight, it's actually computed. Yeah. So it can be run.
Thank you very much, and congratulations again.
Roman, you have a question from the chat.
I go to chat. Yeah. System dynamics. Yeah. So the question is about the system dynamics models and so on. And well, basically, I would say that the system dynamics models are very interesting, and my colleagues, Luděk Berec, is actually using them as well, some kind of models. And so from my point of view, today I was talking about the agent-based model because that's what I kind of like. That's my topic, right? But the agents have advantages. I try to show them, but also some disadvantages. That the model is sort of sensitive, right? Has more perimeters. So what we were doing, for example, for the vaccinations, we actually have 3 different models. We had our agent-based model, we have the system dynamics model, and we have a simple regression model. And when running the experiments, we were sort of running these 3 different models of different nature and trying to get, similar results, or talking about if the results are similar, why they differ. And so my answer to your question is, I'm trying to be pragmatic, and I think that especially in this situation where we're studying the disease, we don't know all the perimeters, we don't know if the data are right, or we almost sure they're not completely right. They have noise and everything. So it's actually better to use different models together and try to compare the results of the approaches. So so I'm totally thinking that the system dynamics model interesting, even as I've said, even for the hospitalizations. My colleague who's a statistician is using sort of, he says simple, but sort of statistical regression models, and they kind of work as well. So yeah, my point of view is, let's be pragmatic. I mean, each model has its own advantages and disadvantages, and if you can run them together and then compare them, the better,
Yeah, as Edgar says, randomness is around everywhere. Yeah, it's totally clear.
Well, I mean, Edgar, if it's randomness, it's sort of okay, right? The statisticians, you statisticians know how to deal with it. You know how to estimate. But if somebody is cheating, like the government is not reporting things or doing like some frauds in the numbers, it's worse.
Thank you, Roman. I have just a small comment. When I saw your graphs of the not forecast about the behavior of the pandemics, the first thing that came to my mind was interval computations. It's like you're not trying to do a perfect fit of the behavior. You're trying to have some boundaries and see what happens according to different scenarios, right?
Yep.
Probably a nice theory to explore will be intervals as themselves, right?
Yep. Yeah. That would. And actually, what we would love to do is to have better of the error measure. If we got some results, how to compute if the results fit. We use the sort of standard error measures. But if we have something more clever, that's probably inspired by interval computing. And the problem with this model is that the traditional approach, you put some intervals into inputs and you got some intervals in the outputs. This would probably mean that you're getting like explosion of the intervals here, because there's lots of like simulation things, right? So I'm not sure if this would work, although it would be interesting to discuss it. But to have at least some, better measures of the fit, not just the standard things, but sort of consider some kind of intervals and so on, this would be interesting.
Yeah, probably. All right. Any other question from the floor? From people?
More than a question, can I do one?
Yeah, sure.
It's still a question. Do you think that improving computational technology and simulation technology, knowing that the model works and the model is by itself, do you think adding horsepower to the computational networks could help develop this kind of ranges, this kind of assessments more quickly?
Actually, yes. Yeah. Because we're actually hitting the limits, right? Like so the simulations I showed you is like say 100,000 agents and a couple million of edges in the graph. If you consider modeling Prague, it would be 1 million agents and 100 millions of edges. If you consider modeling Bogota, it would be what, like 10 million, and some billion of edges. And this would not, we cannot do it on a current computer. So for one thing is that you can do the parallelization to run the individual runs in parallel. Another thing is to have more memory, to fit everything in memory, to not deal with disk operations and so on, and yeah, making the computation faster. This was actually after some time one example where we actually ran into the limits of those computing equipments. Yeah. So definitely, if you make it faster, you can even play with the fits, and analysis of your results, right? So probably to do some good Bayesian optimization, you need more than 1,000 runs, for example, right? Or to have statistically more valuable results, but they take time. Yeah, definitely better hardware.
All right. Thank you very much, Roman, for everything, for giving us your last results here in the conference. So, well, I have to finish the session, and I'm continuing in Spanish. Muchas gracias a todos por estar acá en la charla de Román. Muchas gracias a Román Modjekome. Y
De nada.
entraremos a un coffee break y podremos continuar con las actividades que tenemos para la tarde y ahorita a las 10:30. Oh, coffee.
I have to do more. So thanks again for inviting me. It was a pleasure, and thanks for the interesting discussion. Hope to see some of you in person sometime in the future again.
Gracias, Rafa. Ahora sigue a las 10:30 la charla de William Hutchison. Va a ser muy interesante porque él es una de esas personas con muchísima experiencia y mucho bagaje en el tema de robótica y simulaciones. Así que los esperamos, nos vemos ahora a las 10:30 y en la tarde vamos a tener las sesiones de papers para que pues todos revisen el programa y vayan a las que más les parezcan interesantes. Muchas gracias por estar aquí y nos vemos al rato.
Juan. 1983 desarrolló una alternativa comportamental a la inteligencia artificial basada en ciencias cognitivas o cognitiva. Un sistema computacional basado en ecuaciones de análisis de comportamiento cuantitativo. Este sistema fue uno de los primeros redes neuronales adaptativas y fue el fundamento de una de sus primeras compañías. One of his first. Sí, fue one of your first companies, ¿no?
Yes.
Behave Heuristics, que aplicaba la metodología a software comercial. La compañía se enfocó en el asignamiento de recursos en ambientes que cambian, y una compañía que la sucedió, Applied Behavioral Systems, incorporó el uso de redes adaptativas en robots y desarrollo de software para entrenamiento computarizado de modificación de comportamiento. ¿Cómo diría esto?
De conducta verbal, como palabras, lenguaje, idioma.
Entonces, Applied Behavioral Systems incorporó el uso de redes adaptativas en robots y desarrolló un software que le permitía darle comandos verbales a robots y a niños, ¿sí?
Yeah.
Instrucciones verbales.
Tal vez cambiar verbal behavior to lenguaje o language. Es que
verbal
language, yeah. Well, just language, not verbal. Es que Skinner enfatizó usar verbal behavior para enfatizar es conducta, no es algo diferente.
Ok. Entonces, Applied Behavioral Systems incorporó el uso de redes adaptativas en robots y desarrolló un software de entrenamiento que usaba lenguaje natural para entrenar robots y para modificar el comportamiento a niños, ¿sí?
Sí.
Listo. Hutchinson, no, William. ¿Qué prefiere, William o William?
Sí,
continuó el trabajo, continuó Working Robotics, continuó su trabajo en el área robótica durante un periodo de 4 años en el que trabajó en el Centro de Innovación de Inteligencia del Departamento de Estado, del Departamento de Defensa, ¿cierto? ¿DoD era eso?
Eso es de CIA realmente, pero muchas veces es mejor evitar decir CIA.
Sí, pongamos así nomás.
Sí, mejor. Alguna gente pueden quejar.
Sí, no la quiere mucho. Algo padres del uso de principios de la psicología comportamental y de la ciencia del comportamiento en sistemas computacionales y particularmente en robótica. William Hutchinson está asociado con el centro, el Cambridge Center of Behavioral Studies en Massachusetts, y es actualmente el director de una compañía que fundó que se llama Behavioral Information Systems. Aquí pueden ver el LinkedIn. William obtuvo su pregrado en matemáticas y psicología en la Universidad de Kansas y luego entró al doctorado en psicología clínica de la Universidad Estatal de Nueva York en Stony Brook, una de las más grandes universidades en Estados Unidos, la State University of New York, y uno de los branches más importantes en Stony Brook. Y en esta universidad y particularmente en esa sede en Stony Brook estaba el primer programa de psicología clínica basada en modificación del comportamiento en los Estados Unidos. Esa disciplina del estudio de comportamiento fue comenzada por Skinner y por Pavlov, que es muy famoso. Él nos va a contar algo de eso. Su consejero doctoral fue Leonard Krasner, uno de los pioneros en modificación de comportamiento, economías basadas en token y condicionamiento verbal. También fue muy importante en su formación, en su carrera, el trabajo que desarrolló como asistente de enseñanza de Howard Ratchin, una de las figuras líderes en el uso de análisis cuantitativos de modelos numéricos en psicología y en particular en el estudio del comportamiento. William, al graduarse de su doctorado, estuvo enseñando en uno de los semilleros del estudio radical, del uso radical de las tecnologías de modificación de comportamiento, que era la Universidad de West Virginia, en su programa de doctorado en análisis de sistemas de comportamiento, Behavioral System Analysis. En 1983 desarrolló una alternativa a la inteligencia artificial basada en ciencias cognitivas o cognitiva, una alternativa basada en comportamiento. Era un sistema computacional basado en las ecuaciones de análisis cuantitativo de comportamiento. Este sistema sería o es considerado la primera red adaptativa neuronal y fue el origen de una de sus primeras compañías que se llamaba Behave Heuristics, aplicando estas metodologías a software comercial. La compañía se enfocó, él nos va a contar ahí, en la asignación de recursos, particularmente hubo trabajos con aerolíneas y generó una siguiente compañía que es de la cual soy el director, que se llama Applied Behavioral Systems, que incorporó estas redes adaptativas en el control de robots, diseño y control de robots, y desarrolló software que permitía hacer el entrenamiento de robots a partir de comandos verbales de lenguaje natural y también ayudar al tratamiento de niños modificándose el comportamiento a través de lo que hoy conocemos como terapia, que es comandos verbales, neurolingüística. William también trabajó en el área de robótica por 4 años con el gobierno de los Estados Unidos en un centro de innovación que soporta toda la comunidad de inteligencia en los Estados Unidos, que se llama el Intelligence Technology Innovation Center, desarrollando robots controlados con modelos de comportamiento. William, welcome. It's really a pleasure to have you here, and now you are in control. I will stop sharing. Thank you for accepting the invitation to be in our WEA seminar.
Okay, let me get this working. Let me go back up. Slideshows. Now, first, let's see. I'd like you to see me first. Can you see me in the little window?
I'm seeing your face and seeing the presentation, but it's not full screen. It's like with the Windows background.
Yeah. Here. There we go. I'll start the slideshow in just a minute. But I'm very happy to be back in Colombia, even though it's virtual. I was a professor there for 2 years in Bogota in the Universidad Católica. And then 2 years ago, I taught a week-long course at the Universidad Nacional about the same contents that we'll talk about today. And I have many fond memories of being in Colombia. So I'm honored to be invited to present this paper. Sí, y perdóname por presentar en inglés, pero es más fácil y Doctor Hernández me aseguró que todos pueden entender inglés bastante, pero I've made the slides to contain more of what I'm saying so that you have more cues for those that are not really strong in English. Okay, let me start this slideshow from the beginning. Okay. So, as all of you know very well, there's a long history of engineering solutions that are discovered by studying nature's solutions to related problems. So today we'll talk about one of the most striking cases of that, which is emulating human-like intelligence in robots. So until a few decades ago, computers had to be programmed based on logic. Then about 40 years ago, several theorists, including myself, figured out how to make computers learn from experience like animals learn. So today we'll be looking at reinforcement learning. Many of you are familiar with that already, but it was inspired originally by behavioral science research on the most important type of animal learning called operant conditioning. Now, all of you are very well familiar with the basic idea of reinforcement. If an animal does something you want, and if you give it a reward, then the animal will tend to do the same thing more in the future. And the opposite of that, if the animal does something you don't like and you punish it, it's less likely to do that in the future. So we'll take that concept and elaborate it. You already heard some of my background there, so I'll just mention it briefly. So mathematics and psychology both feed into this. Then, of course, I needed to learn how to do programming, which was fairly new at the time, back 40 years ago. Then you already mentioned my main advisors, where I acquired the mathematical learning theory and language analysis. And in this program, it was unusual in that it was the first program to teach clinical psychology applying to humans based purely on the radical behavioral analysis, not Freudian or cognitive, which was dominant up till then. In fact, one of my classmates was Leonidas Castro. Some of you may know him in Bogota, very accomplished psychologist. So now we had these equations from behavioral research. So I got the idea that if those equations are correct, and if I programmed them into a computer, then the program should learn like an animal. And it worked, almost surprised me. So this idea was considered rather crazy at first, the idea that a computer could learn. I offered it to my employer who was doing defense contracting, had many applications that would have been great for it, and they refused it. And I would say that was a big mistake, because now it's one of the most important technologies in the world. So let's look at reinforcement learning in animals. The central concept we already introduced is that the strength of behaviors is changed by their consequences. So we'll look at several fundamental and powerful extensions of that simple concept, because the simple concept doesn't explain some important facts about learning that we have to take into account. The first is discrimination. If you reward the behavior in one situation and not in another, the animal will learn to do the behavior only in the rewarded situation, showing that it wasn't just the behavior that was strengthened. Generalization: if you have a situation that is not the same as in your original training, but similar, the animal will tend to do the same behavior in the new situation. So to explain those phenomena, we need to recognize that what is reinforced is not just the behavior, the action, but the connections or associations between the current features of the environment, known as stimuli, and the behavior. So the idea of those connections is where we get the concept of a network of connections between stimuli and responses. So this is the simplest possible network. The biggest network I did, that I'll mention later, had 1 million connections, but the basic concept is the same in this simple network. So for many of you, this is already very well known, but so the inputs to the network are the sensors for the stimuli, and the outputs are the behavior. Then those connections in a brain are neurons, but in computer reinforcement learning, the connections can be simply represented by numbers. Now, there are many algorithms for how to do learning, how to change the weights. Learning is based on changing the weights in the network. So you see, I've got 3, 4, 4, 1. The simplest approach possible is to multiply each input value by the connection value and sum those for each of the outputs. Then the highest value dominates. Although, of course, you can have more than one behavior at the same time, but let's stick with the simple situation where the strongest one wins. So you can do the calculations very easily up there. You see the input 1.0 times 4, and the output, you have a 4, and then at the bottom, the second input is 2 multiplied by the weight of 1. So 4 plus 2 equals 6. And for the R1, then it sums to 5. So response 2 would be the one that was done based on those weights. Now, in learning, the connection values are incremented or decremented. Now, which connections do you change? So just apply a little logic to it. Reinforcement is applied only to the connections between the current or very recent inputs and the current outputs. That issue is called credit assignment, because those are the connections that caused the behavior. You wouldn't change weights for a stimulus that wasn't present. You wouldn't change the weights for a behavior that wasn't done, because those aren't what caused the success or failure. So here's the diagram of a complete system. I'll leave part of it out, but you see we have sensors. Sorry for the blurriness of it. You have the sensors. Then there's usually sensor pre-processing, especially for things like vision or sound. Then it passes through the network that we just looked at how that happens. Then there's an action selection system, which might be as simple as, select the highest valued output. And then those get connected to actuators that do something in the real world. They may just output the numbers, but on a robot, of course, they would actuate the robot movements. And the learning process down at the bottom changes those connections. Now, as you know, most networks these days also have nodes in the middle that connect more than one input and then go to an output. But for the purpose of today, we don't need to worry about that. And then we'll look more at those other elements of the learning system in just a minute. Okay, now how do we train a reinforcement learning network for a real world problem? Okay, to train it, we take an example from our target environment, and we have a set of inputs. We apply those to the network, we activate the network, which in the simplest case is just to multiply those values, and then we pick the strongest output. Now, how do you reward a computer? Computer doesn't have pleasure or pain like animals. So B.F. Skinner solved this problem, solved this question from a scientific viewpoint. But instead of basing rewards on pleasure and pain, he invented the technical term reinforcement. Of course, the word existed, but he picked that as the preferred word rather than reward. Reward has too many implications to it. So reinforcement is anything that strengthens behavior, and punishment is the opposite. So if an output is correct for your application, then you increase the numbers connecting the inputs that you presented to the output, the connections between the inputs that you presented connected to the output that was chosen, just as we discussed. Otherwise, you decrease the numbers if it was wrong. Now, you need a set of training examples. Often people talk about, well, you need so many cases that defines the complexity, but actually the ideal way to do that uses concept analysis from applied behavior analysis. You analyze the relevant positive stimuli, things that must be present, and the relevant negative stimuli, things that must be absent, or things that must not be present, and then irrelevant stimuli that could mislead. And then you present all combinations of these to create a set of positive and negative cases. So here's an example. You've got a robot that should be picking up mugs from among other food dishes. Say it's going by on a conveyor belt. So the relative positive characteristics of a mug are it's concave downward and it has a handle. The relevant negative would be if it's short, like a plate, or narrow, so it can't hold anything inside of it. An irrelevant, a really key irrelevant characteristic is color. So in random order, or some variation of random order, you present the positive and negative examples and you reinforce only the positive ones. Now with animals, you probably know, with animals and children, you try to avoid punishment. You stick with the positive. But with computers, we don't have any ethical concerns about punishing the computer, decreasing those values. And you see why we have to consider irrelevant, because if, for example, you used only red cups for your in your training examples, the system would have no way of discriminating or disambiguating what really was the key, and it could instead learn that red was correct, whereas actually red is irrelevant, so you need to mix the colors. So what was my first real world test of this? When my employer, well, I was still working for the US Army Research Institute, or working for a contractor for them. We were developing a logic-based program called INCOA, the Enemy Course of Action. This is the Army after all. So to predict what the enemy military forces would do based on the available intelligence data. So the AI technology at that time was symbolic AI, expert systems. So that was based on human judgment, human rules. Now, this is a very challenging problem to predict your enemy's behavior because they're always trying to deceive you. They're doing actions, they will intentionally do actions that appear to indicate one course of action, but then they do a different one. So to train it, I created a bunch of examples by surveying human experts in this field. Then I trained the system using those examples, and the results were that it matched the performance of those human experts. Then if I pooled all the examples from all of the experts, it outperformed all of them. Well, that was pretty encouraging because this was an important application. So I formed a company along with another behavioral psychologist to apply this technology. That was behavioristics. We get blamed a lot for that name. We thought it was pretty cute at the time, combining behavioral and heuristics. We did a variety of applications, asset allocation. We applied a swarm of reinforcement learning agents to do scheduling, and we did speech recognition. So, but our main application was for airlines. The system would learn their demand patterns and would allocate the seats to different booking classes that had different prices and restrictions so as to maximize the airline's revenue. Now, our biggest customer was US Air. They had a big problem. They had 5,000 flights every day, and each one of those flights was booked in advance, 365 days, a full year. And each of those flights had 8 booking classes. So we had a total of 15 million things to optimize. So the main goal was to learn the demand patterns and make optimal trade-offs between the high probability sales at low prices, that is a discount class, and a lower probability sale at a higher price, like a business customer, he's going to book at the last, but it's lower probability, but you're willing to accept. You see, you could balance that out. If you had a 1/3 probability of selling that seat at a high price, it would be worth as much to you as selling it today for the low price, for $100. Now, what were the inputs to the network to learn those patterns? So we had the origin city, the destination city, the day of the week, the time of day, the time of the year, and the number of bookings so far. So first, we trained the system on 2 years of data, 50 gigabytes, which at that time was a big challenge. We had a room full of RAID array disks to hold 50 gigabytes of data. Now that would be pretty poor for a laptop computer. Then we created a network, a huge network, by linking the 200 workstations that the US Air marketing people used into a huge network with 1 million connections. We got a Smithsonian award for that design. And this was the largest reinforcement learning application in the world at that time. Now, we kept the network, the prediction network, updated by training on the very latest data each night using their computers that the humans weren't using. And then the next day, we would provide the recommendations. So the system was very effective, and it earned US Air $140 million in its first year of operation, according to their auditors. That was pretty big. That was quite a positive vote for this technology. Now, there are many valuable applications of that simple system that, I outlined how a simple reinforcement learning network works, but there's a fatal weakness for many applications. That is, in this network, learning depends on getting an immediate reward or punishment for the action. That, as you know very well, in the real world, most interesting behaviors, valuable behaviors, don't produce immediate results. They require a series of actions to finally produce the results. So it was a big breakthrough to, again, dip into behavioral research with animals to find a solution to that problem. And it's known as conditioned reinforcement. Those of you that have studied psychology know that concept. That is, animals can be rewarded not only by so-called primary reinforcement, that is like food or water at the end, when they do the final behavior, but also by learning the stimuli in the environment that predict progress toward the primary reinforcement. So at each step along the sequence of actions that have to be done, the animal implicitly evaluates the state of the environment. We call that situation value. If the situation value goes up, that functions as reinforcement, just like primary reinforcement. Now, how can the animal or the computer system learn the values of the situation? They're based on the primary reinforcement, and they get backed up from the final step where the reward is delivered. In behavioral psychology training, we call this backward chaining. In computer reinforcement learning, this is commonly referred to as temporal difference learning, because you're taking two different times. One moment when you do the behavior, and the next moment when you have the new situation which you evaluate. As an example from the game of checkers, which was actually solved back in the early 50s, you start with the board position just before the final move that enables you to win. Okay, so when the computer or the person, but in this case, the computer, when the computer makes the correct move from that final position, they win and they get reinforced. Then you back up one board position. You back up to a case where a move can put you in the situation that you just experienced. So you have to take two steps. You have from that backed up position, you make one move that puts you in a position where you can make the final move and win the game. So the conditioning gets backed up from one situation at a time, and you can back up all the way to the start of the game. If you were teaching a child to tie their shoes, then you tie the shoe for them all the way except for the final step, maybe pulling the two sides. They pull the two sides, they have success, then you back up to the step before that. Okay, now this reinforcement learning should obviously apply to robots, because robots do actions in the real world similar to humans. So there are a huge number of valuable applications for robots. And for many of them, they're easier to learn than to program. I certainly found that out. I would always try to program it first, and when I would finally give up, then the learning would master it quickly. And the demonstrations of learning with robots are much more interesting and convincing than pure computer applications. So it's relatively simple to implement robot learning in a robot. I wasn't sure of that when I started, but it worked very well. The inputs to the network are provided by the robot's sensors. Then the robots perform actions. You have a network that links those. Now, the biggest problem that I saw was how to operate in continuous time, because reinforcement learning is based on a sequence. So you simply do cycles of, you have the inputs, you do an action, and you learn based on the results of that action. And how fast are those cycles? It depends on the application. Some applications, you could be one cycle per second if it's a slow moving robot, let's say. But if you were doing a language-based application, you need to have maybe 15 cycles every second in order to process the speech, the phonemes. So now we need to very carefully choose what the reinforcer is going to be, because that'll determine what actually gets strengthened. For example, MIT had a laboratory robot that moves around the office collecting empty soda cans. So in that case, the reinforcer is the soda can. If a robot is supposed to climb, then altitude is the reinforcer. So now we're interested in autonomous robots. Instead of an external teacher that delivers the reinforcers, then you equip the robot with sensors for primary reinforcers. For instance, in those previous examples, it can sense the soda cans or it can sense its altitude. Plus, you need a mechanism to process those sensors to determine value, like humans have. The ventral tegmental area of the brain takes those stimuli and evaluates whether it's a reinforcing condition or not. Here are some of the robots that I've worked with. You probably recognize the Roomba. Then we have the Garcia laboratory robot. Then the one I worked with most is the Serpentine robot that you see at the right, a very complicated robot. Then the LRV, a reconnaissance robot on the lower left. Then the IBO robot, the dog robot you are probably familiar with. And then a hexapod robot. So those were the main ones that I've worked with, but quite a variety, and reinforcement learning is very good for all of those. Okay, what are the challenges in getting control over robots? Reinforcement learning is the most advantageous for robots if their behaviors are difficult to program. If you've got a simple behavior, you don't need to use this technology. You just program it, it's going to be very reliable. But if you have a complex natural environment, it's difficult for a robot. And most human environments are complex. The second is the complexity of their movements. The robot I did most of the research with for the Intelligence Technology Innovation Center was the Omni robot. You saw the Serpentine snake robot has 22 degrees of freedom. Now, a serpentine robot is much more difficult than a legged robot with legs, because with the legged robots, each leg movement is mostly independent of the other legs. Whereas with a serpentine robot, the segments are all connected. So every movement affects not just that segment, but it affects much of the rest of the robot. So a prototypical problem for this robot is to climb stairs. That's what we would typically start with to see if we've got something that's going to work in a complicated environment. So let me show you, let's see, let me drop out of this and bring up some videos. Okay, first I'm going to show you a sequence of learning. So you can see there'll be six stages, and at each stage, the robot has been exposed to more learning. So this is the first stage. Doesn't get very far. Gets about that far, and then it gets stuck. Second stage, it's been exposed to more learning, gets up one step, but then gets hung up. Then it learns to come from a slight angle, but falls over. Okay. Then the next step, it's learned some more. So it gets up 2 stairs, then falls over again. The fifth stage, more learning. It's doing much better, but not quite. Okay, the final stage, you'll see it masters that problem all the way up to the top. Now, of course, this is a simulation. So next, you really need to develop the robotic control, the learning, in a simulated environment. Let's see. Let me figure out how to get, let's see. Sorry, I practiced transitioning. Just a minute, I need to stop this. Okay, so you need to train in a simulator, but then it needs to be a very accurate simulator because you're going to apply it in the real world. So it has to do the same thing in the simulator that it'll do in the real world. So look at this video. You'll see here's the real robot. climbing a set of stairs. And you see the simulator in the lower left that predicts, it learned in the simulator, and then we put it in the real environment, and you'll see the two sequences, the behavior in the simulator very accurately predicts what the robot's going to do in the real world. In fact, it was better than the human operators at predicting what the robot could actually do. You can see this is a more difficult environment than simple stairs. You had to be able to go across fairly long gaps, which is a strength of a serpentine robot. Be able to, it's about the most versatile kind of robot for different kinds of terrains. Okay.
Yeah, it's good.
Okay, that was the developer of the physical robot. Okay, let me. Okay, next. I'll show you lateral movements are more difficult because you don't have gravity naturally working with you. So this is the same robot in a different simulator learning to, this ramp is too steep to climb. So it has to learn how to use the posts along the way. And you see, it's really interesting how reinforcement learning develops behavior that looks very organic. That really looks like that might be a real snake trying to get up that ramp. Okay, and then we need to be able to do realistic environments. So this, it's still a set of stairs, but we put a bunch of obstacles in the way. And I'll jump ahead here because this goes on quite a bit. So you can see how it's combined the knowledge about climbing vertical barriers with using the lateral affordances, as they call them, lateral stimuli. Okay, and let's see. Then finally, I just want to show you a little clip of the IBO. Let's see, here we go. The IBO is actually, it tips over very easily. So that when they've had contests of IBOs to do different tasks, a lot of times nobody even enters the one to climb. So you'll see this gets, each step is a little bit taller than the previous one. So this IBO, we developed this with the Draper Institute. It can almost get up to the top. Not quite, that's how far it gets, and then it gets stuck. Okay, let me quit that. We'll go back to the PowerPoint. Okay, just a minute. Let's see, I want to continue, but that is blocking. Here we go. Slideshow. Continue from current. Okay. Now, another major challenge for reinforcement learning, but especially for robots, is that there are a huge number of parameters to decide. You know, these meta parameters they're commonly referred to. So why are there so many? You have all the sensor and pre-processing properties. You have the robot body characteristics, you have the motor movement properties, you have learning properties, and you have training program parameters. So you may end up with we often had 300 parameters. So for example, just for vision, we needed to specify the horizontal and vertical fields of view, how wide and how tall, the resolution, including possible foveal resolutions. It's very advantageous that you have a higher resolution in the middle of your visual field, like humans have, and like modern video games often have. You had to decide the color characteristics, the frame rate, and pre-processing parameters, for instance, edge detection, normalization. So developers like me can spend a huge amount of time testing the ranges of values for each of these parameters in order to optimize them. But you can do them one at a time, and that is still not sufficient because many of these parameters depend on the value of other parameters. For example, the optimal visual resolution depends on the kinds of pre-processing that will be done, among other things. The optimal arm motor parameters depend on the physical properties of the arm that should also be optimized. So this makes optimization of the parameters a combinatorial nightmare. You could have thousands of combinations that need to be optimized together. So we're fortunate. We go back to nature. How do we solve that problem? How does nature solve that problem? And that is a combination, the synergy of learning and evolution. How do these parameters get set in the natural world? The parameters of animals get determined by evolution over thousands of years, millions of years. And some robotics practitioners consider learning and evolutionary methods to be alternatives, but nature shows us that that's not the case. They actually work together synergistically. So evolution over thousands of years determines the fixed characteristics of animals. Then learning operates within those parameters during the animal's lifetime to adapt quickly to the immediate contingencies in their environment. So optimal learning and evolutionary parameters are totally dependent on each other. So they need to be optimized together. So I implemented this combination for developing robotic control systems, and it works extremely well. That's actually the only way I could solve those difficult robotics problems like the snake problem that you saw. So many of you will be familiar with genetic algorithms that are meant to mimic natural evolution. So each of the parameters, let's say those 300 parameters that are going to be evolved, gets specified as a gene with variable values. In other words, you don't know what the values are going to be, so you allow that to vary. So the genetic algorithm starts by creating a population of instances with varying parameter values. In other words, each one is different. It's best as a practical matter, it's best to start with the developer's predictions of reasonable values. If you start with random values, the system is going to spend a long time just getting into a reasonable range, and there's no need for that because you can start from what the developer predicted, and the developer could be wrong, but at least the GA will gradually reach the optimal value. So you create a new agent. This is your learning cycle. A new agent gets created by selecting two parent instances. And you bias the selection of the parents by their fitness. That's in nature. The more fit the parents, the more likely they are to be selected or to survive. You select some of the parameters from each parent. That's called crossover. That's as happens with animals. You get some of the genes from each parent. Then you mutate a certain fraction of those parameters by slightly changing their values. And mutation actually is a pretty minor part of this. It's necessary, but it usually is a very small amount of change. Then you place this agent into your simulated environment that will train it to do the target skills. Then you evaluate its fitness. What is fitness? It's how well does it perform the target task, and likely other criteria, such as how fast it learns. Now, there are two robots that learn as well, but one learns faster. Is the faster one's going to have higher fitness. Then if that one that you've just tested exceeds the fitness of the least fit member of the population, then it replaces that, less fit member. That's not the way GAs are always done, but that's called elitism. And given the very high computation intensity of this GA plus learning, then that's much more efficient than you replace the entire generations, as it sometimes does. Just an example, if you have a basketball player, if you have Michael Jordan, in the next generation, he's died off, you've lost, your best agent. So elitism is much more efficient. So it's essential to optimize the physical robots and the action learning system together, because each depends on the other. And explaining that, the effectiveness of the physical robot depends on how skilled its behavior is. And of course, the effectiveness of the behaviors depends on the physical characteristics of the robot. So even for people that are just designing physical robots, this combination is a very desirable way to design the robot, because the best physical design depends on the behavior that it's capable of learning. Okay, now we've talked about these huge leaps in capabilities beyond simple reinforcement, the thing we started out with. The first was conditioned reinforcement, so that we could learn sequences of actions that had delayed reinforcement. The second major leap was the combination of genetic evolutionary technology and reinforcement learning technology. Now, let's look at the most revolutionary advancement of all, and that's yet another based on nature. Okay, the single most important capability where humans can far exceed the capabilities of other animals is language. So if we want robot learning to be much more powerful, we need to incorporate language. We humans have vast repertoires of behaviors that we did not have to learn individually from experience. We were instructed with words. So many of these skills that we've learned would be extremely costly to learn by experience, even getting into those situations to learn, but they're very easy to instruct. And many behaviors are too dangerous for people to learn by direct experience. You wouldn't learn to drive by going out and being successful or having a lot of crashes. But you can be quickly instructed using language. So then finally, most valuable human behaviors simply cannot be learned by trial and error. In other words, simple reinforcement learning. You drop the agent into an environment and expect them to learn just by success and failure. Why is that? Because they have to do the entire sequence of behaviors correctly in order to receive reinforcement. And that sequence would never be discovered, or virtually never be discovered, by trial and error, because extinction, you'd be punished for many errors along the way before you finally had one instance of success. That ratio doesn't work. So now, that seem to contradict what I said before. Conditioned reinforcement enables learning a sequence, but only if the agent performs the sequence perfectly. So verbal instruction using language that enables you to perform the sequence perfectly, even the first time, and get reinforcement. So language is extremely important. I mean, that's almost goes without saying, but I've analyzed why it's so critical. Now, how do you give a robot natural language? We have some really impressive natural language processing systems now. And those could be connected to a robotic system to give the robot language. But that would require integrating another different technology. It's not reinforcement learning, or at least it's implemented very differently. It's complex and extremely compute intensive. So fortunately, we have a simple and intuitive way to teach language to a robot that's based on reinforcement learning. And this approach is based on the analysis of language by B.F. Skinner many years ago. So again, we come back to Skinner, who was the pioneer in operant conditioning. The advantages, if this works, the advantages are we don't have to have any new architectural elements, no different natural, NLP system to develop and to integrate with the motor behaviors, just the existing RL. Secondly, the advantage is it can be taught to the robot using the same methods as teaching language to children. We know how to do that, so we can use the same technology. So, and finally, when it's implemented this way, you naturally get the interaction between language and the motor behaviors, just like with humans. So I have done many tests of this analysis. It's actually my greatest interest, and it works very well. Okay, let's look at how to train language. Humans start with pre-linguistic behavior. What is that? That's to imitate sounds made by others. Those speech sounds are called phonemes or phones. And the behavior of imitating, Skinner calls that echoics. You can see echo. And those are necessary to learn as a foundation for later language learning. Now, it's actually easy to teach echoics to a reinforcement learning system. The robot has to have the capability of making sounds, of outputting sounds. You present a phoneme sound to an agent, in other words, to the microphone. There's always pre-processing of sound where we pre-process it like is done for speech recognition, which sort of imitates how the brain actually, how the ears and brain actually process sound. So we present that sound to this network, and when the agent, in this case an agent or a child, makes the corresponding sound, we reinforce. Okay, so it hears ah, and it outputs ah, and you reinforce, just like you would do with a child. Now, this is mostly trial and error learning, which could take a long time, but fortunately it's for a limited set of behaviors, maybe 28 phonemes, something like that. There's also a trick that can accelerate that quite a bit, which a lot of parents learn that trick, but I won't get into that right now. Okay, so let's assume that the system has learned echoics. The initial behavior, the initial language behavior that infants learn, and then we want our robots to learn, is to name things. That's the earliest language. Most parents have learned from experience how to teach naming fairly efficiently. I'm sure most of you could do it. You show the child something. Let's say you hold a ball in front of them and you speak its name. This is a ball. So, and you start with short words. Then if the child has learned to imitate sounds, then they can repeat what you said. You said ball, they've learned to imitate your sounds, so they say ball. then you're a happy parent. You reinforce the child in some way. You know, naturally you are inclined to reinforce because the child has just done what you wanted him to do. So you praise them, you hug them, or maybe you give them something. So this same procedure can be used to train names to a robot. Now, it seems like naming is a pretty limited function, but actually it's extremely general because look, when you name a thing, that's a noun. When you name an action, that's a verb. When you name a property of things, like its color or shape or whatever, that's an adjective. When you name properties of actions, like the speed, how fast, that's an adverb. So you've covered, with simple naming, you have covered 4 of the core language functions. And all of them are learned by the same simple process. So just technically looking at what's the analysis of these. Now, Skinner called these tacts. He wanted to always choose technical terms so that we wouldn't have the baggage of natural terms. So we wanted a scientific term. So you can see that's derived from like contact. The sensory stimuli are to see the thing or the action or the property, and at the same time to hear its name from the teacher. The behavior is to imitate or echo the name that was heard. The reinforcer, the teacher provides that, as we talked about, a hug or something tangible or just praise. Now, that doesn't seem to get you very far because the child is simply imitating the sound that they heard. So at first, seeing the ball doesn't help to say ball, but the stimuli, the visual stimuli and the sound are presented at the same time. So when the reinforcement is delivered, it strengthens the visual stimuli that were initially neutral. So the control, the technical term is transfer. The control is transferred to the vision from the sound stimuli. So after just a few trials of this, the child can name the object without help. You fade the, we call it fading, the sound stimuli. So you say it softer, or you delay or whatever. And after a few trials, you know this perfectly well. After only a few trials, you can learn to, the child can learn to name the object without the cue. So now let's look at another category of language. It's also very broad. Skinner calls these intraverbals, and the name suggests, you know, it's words associated with other words. So there are 2 main cases. One is rules or instruction or advice. If you sense X, do Y. In other words, if the situation is X, then you do Y. So, you know, if you see a red light, stop. The second is facts or knowledge. So some examples: 2 + 2 = 4 is an intraverbal. The capital of Kansas is Topeka. Oil and water do not mix. Joe's birthday is May the 4th. Sugar is bad for diabetics. Okay, the analysis of intraverbals is also very simple for a reinforcement learning system. The stimuli are words. The behavior is to say the associated words. The reinforcer, when you're being taught, it's explicit from the teacher, or very often, if you get it right, then there's a value that's naturally produced by following, you know, by the behavior that follows the intraverbal. So you succeed, you followed a rule, you succeed. So the reinforcement is natural. And finally, the third one we're going to consider, the last one, is pliance. You can see it comes from the word compliance. That is performing a verbally specified behavior. For example, the child hears sit down, and they do it. They sit down. So the stimulus is hearing a command or instruction or request. The behavior is executing the behavior that is specified by the command or request. And the reinforcer is either provided by the requester, which is referred to as power, or by the natural positive result of the behavior, authority. In other words, if you follow a request or an order because the requester is going to reward or punish you, then that the behavioral sociologists refer to that as power. You do it because of them. Or if you hear somebody say something and you do it because you've learned that that person is smart, when you follow their advice, the world is going to reinforce you. So the behavioral sociologists refer to this as authority. Okay, now, surprise. We get a wonderful serendipitous effect. When you've learned tacts and interverbals and pliants, they link together naturally and allow you to do wonderful things. With no additional training, these three verbal functions combine to enable extremely valuable behavior. For example, a car driving robot, let's say you've taught it to tact red lights. It's learned the interverbal rule. If you come to a red light, stop. Then pliants, it's learned to stop when it hears the command stop. Okay, now let's see what happens after you trained those three behaviors. Robot's driving, sees the red light, it says red light, a tact. Now, its own saying red light triggers saying stop because it learned that association. Then saying stop triggers stopping. In other words, that was pliants. These chain together naturally with no further training, and they can link to more elaborate chains that enable a lot of language. So you can see, well, people don't, or a robot wouldn't just go around following really simple rules. More commonly, the interverbals link to other interverbals. We refer to that as thinking about it. So before finally performing the action at the conclusion. For example, you tact Wednesday. Today is Wednesday. The interverbal is, oh, Wednesday is trash day. Then another interverbal, trash day, put out the trash. And then pliants, you actually put out the trash. So you didn't just have one interverbal. The interverbals chain onto each other. Then also tacts can combine nouns and adjectives. So you specify the stimulus condition more narrowly. So it wasn't just red, it's red and light. Finally, the pliants action can consist of a sequence of intraverbal actions that get executed when speaking the sequence. In other words, it's not just stop. You can get more complicated than stop. For example, if your sink is leaking, turn off the valve, unscrew the handle, remove the washer, and so on. So your interverbal can specify a number of actions, which then you execute by pliants at each step. So in summary, tacts and interverbals trigger saying other interverbals like synonyms, reasoning, other facts, rules that specify a behavior or sequence of behaviors to carry out a procedure. So what's the advantage of doing this approach to language instead of the big natural language processing systems? First, you can get powerful language abilities without adding on a different technology, an additional technology, especially a very complicated compute-intensive technology. Second, you can teach language to robots using methods like we use with humans. Third, the language that they've learned integrates naturally with the other language functions and with the motor behaviors. So you don't have to figure out how do we connect language to action. It is automatic through the pliants. And the final step is, the final advantage is after you've learned a set of tacts and pliances, then you can learn new rules or information simply by learning the intraverbal. You learn that one key, the intraverbal links the tact to the action. So you've learned a set, and they can be combined in all different combinations, like I refer to as connecting Lego pieces. So you can very rapidly extend your verbal repertoire. Okay, the final slide here. So reinforcement robots, RL robots, can receive reinforcement from external sources, but also can have their own values that ultimately control their actions. This makes them autonomous. What is required? We went through this before. To be autonomous, it has to have sensors to detect the occurrence of the valued events, to detect like altitude or soda cans. Then you need an internal mechanism to evaluate those events and calculate a value to trigger reinforcement. You need to think through very carefully what those values should be to avoid unintended consequences. An interesting case that I had, I trained my robot to follow my commands. So it would hear my command, it would execute the command. It had sensors for my speech. It also had a sensor for pain. When it would collide with something, it would feel pain, which was a punisher. So I taught the robot to follow my commands, how to move around and get rewards from me. Then I commanded the robot to crash into the wall, which it did. Then I commanded it again to crash into the wall, which it did. The third time, I told it to crash into the wall. It went forward and it stopped and turned before the wall because of the pain that it had suffered from the crashes. So it disobeyed me because it was an autonomous being. That's what an animal would do, of course. And that sort of negative consequence of autonomy was dramatized in movies like 2001 Space Odyssey with HAL and iRobot, where the values that were programmed in the AI system led them logically to harm humans. That is going to become more and more dangerous, in my view. With technology progress, computers are getting more powerful, the robots are getting more effective. Then if you combine that with these evolutionary methods of learning that I've been laying out and language, I cannot see why robots will not eventually surpass humans, and based on those examples, how they could potentially control us. Now, you may already have in your mind how we can avoid that. And there have been a number of solutions proposed. I don't believe any of them work. I've analyzed all of them, but we must solve it, or we've committed the ultimate folly of creating something that is going to harm us. So that's my presentation. As you see, the reinforcement learning technology can go a lot farther than it's typically being applied these days. That's been my specialty, and behavioral science has enabled those advances. So I invite questions and discussion.
Thank you very much, William, for the presentation. Then please raise the hand if you have a question that you want to do. You can do the questions in Spanish. William is able to understand the questions in Spanish if you want to do the questions in Spanish, or you can post the question in the chat. Pueden poner las preguntas en español o pueden en el chat, o las pueden hacer en español. Levante la mano si alguien tiene alguna pregunta para abrirle el micrófono. ¿Alguna pregunta del público? Okay, I have one question.
Okay.
there is this social learning and there is this cultural optimization algorithms like the ant population that are like based on cultural things. They are sometimes combined with the evolutionary ones, but they call them like cultural learning algorithms. But in humans, it seems like culture is learned through language, to things that the whole human population has learned. I don't know, democracy as a way of government, ethical frameworks of what to do or know what to do, and those are taught in the schools. Then this language will allow to have this cultural learning embedded in robotic beings if you give them, like, I don't know, ethical principles, as you were mentioning, via language, and also continue evolving. Then they will evolve faster than human populations combining those sources. Is that possible?
Yes, that requires another level of modeling. So we've now looked at the evolutionary development along with learning for individuals, where we've got a particular task in mind. I early on applied a set of robots that would work together to schedule. So they would learn to bid for resources. And also we developed a model for Steelcase. It's known as an office furniture company, but they wanted to develop a technology for changing their company into a productivity company. So they wanted software that would optimize the management system. There's all the connections between people. So to do that, you have to create a set of agents, each with their own behaviors and their own rewards, and link it all together into a big complicated system. So yes, you'd model culture that way. So you wouldn't just look at the behavior of one individual. I mean, a classic example is called the tragedy of the commons. That is, when you have a community that has, let's say, sheep. Everybody has their sheep, and you have a common area in the middle. Each individual having as many sheep. Everybody does that. It destroys the common area because it gets overgrazed. So you could model that and see, what ends up working the best for everyone. So you'd have to have rules for, how many animals each person could have and so on. To optimize that culture, you could model the system, with multiple agents. But you're absolutely right. Culture is conveyed by language. So we're standing on the shoulders of giants.
Okay, we have a time for an additional question. Is there an additional question? If no, we will.
I got one.
Okay.
Go
ahead.
William, have you had the opportunity to work with fuzzy sets? Because fuzzy sets are really, really into the meaning of words and how to emphasize the meaning of some words using different kind of mathematical entities. Have you had the opportunity to work with?
What kind of set were you saying?
Fuzzy sets.
I guess I haven't.
Those try to involve, like, you have like statements that or concepts that are true or false. Like, let's say something is white or is not white. But in human language, you have ambiguity. Like, you could say hot, and I don't know, 300 degrees is hot, and I don't know, 0 degrees is not hot. But we humans use in reasoning ambiguity, and that's a kind of logic, fuzzy logic and fuzzy sets, that allows to model the ambiguity and do reasoning with ambiguity. It's a complete logic to do reasoning with the ambiguity that we use in human languages.
Yes. Sorry, I misunderstood. I didn't understand fuzzy. Yes, fuzzy logic, and that's certainly completely amenable to implementing in a reinforcement learning system. I don't know if I could try to elaborate on that right now, but certainly it's quite feasible for a reinforcement learning system to learn a fuzzy concept, which would be, based on the characteristics of the inputs and, what the consequences are of, it would be more complicated than simple cases like, that's red. Well, it's not quite red, it's kind of orange. That would be an example of fuzzy. So it depends on we would say the verbal community teaches those subtle discriminations.
Yeah. I've seen some papers working on some reinforcement learning applied to some fuzzy logic systems. But didn't read the papers, but I've seen some people working on, but not really sure what they're doing exactly.
Yes. Well, as I said, my main interest in all of this, even from the beginning, has been on learning by reinforcement learning systems of language, of real natural language. And Skinner's analysis goes beyond. I presented the three core functions, language functions, but he analyzes the entire spectrum of language. It's a book called Verbal Behavior, and it's very interesting because you've got other cases like not, or as you'd say, some, all, a few, lots of challenges, but Skinner made great progress on analyzing all those from a reinforcement learning perspective. He wasn't thinking at the time about computer reinforcement learning, but it applies directly. It's a very fascinating field, very almost limitless right now.
And there are like concepts in cultural like learning or social like cultural learning that are sort of fuzzy. Then is something that is going to happen if we allow robots to learn from language. They will have to model these concepts like few or things like that are part of the instructions are in the laws and in the rules of society and things like that are already involved, and you have to learn what's that concept that is not precise but with ambiguity. Then it's unavoidable. If you are going to say like to a robot, go faster, how much is faster if the robot is driving a car? Then it's sort of unavoidable to use the learning of those ambiguity concepts, like with fuzzy logic or whatever. That will be the tool now for like the future robots, and also to learn using cultural things that are with ambiguity. Do you think that's a fact?
Yes, definitely. And you can, when you think about how do we do this with a robot, you can see my philosophy all along has been go back to nature, go back to how this works in the natural world, which in the case of language would be, how do humans learn that? You say go faster, the person has had to learn what does that mean? And in fact, in a particular case, they may not do it right. And they may have to be corrected. Go faster. No, I didn't mean that fast. Slow down. So it's on problems like that, I would always go back to the human case and to, as much as possible, actual research on these phenomena. The field of behavior analysis has a lot of knowledge that most people don't know. Even people in reinforcement learning are by and large not familiar with the scientific research done by behavioral psychologists.
Okay, is there any other question? ¿Hay alguna otra pregunta? If not, we will thank William for this really nice talk. Gracias, William, por esta presentación tan interesante con nuevos. Every year you add new new insights that are very interesting, pointing towards the future of the use of behavioral sciences in computing, artificial intelligence, robotics, machine learning. And it's really a pleasure to have you here. Thank you very much. ¿No hay más preguntas? Okay, thank you.
Just one.
Just one? Okay. Just one, the last.
Well, the lecture was quite interesting, Mr. William. I just want to ask you if you think that behavioral networks for robotics can be easily interacted with. With that, I mean, for example, using ROS, the robot operating system, how easily can be used, how easily can be applied.
Could you clarify how easily could you use this robot learning?
For example, the method that you describe using registered activities based on what I must refer to Pavlov method.
It was mentioning a robot operating system, ROS.
Yes. It's
it's easy to implement the behavioral networks. Is a complicated programming if we try to use like robotic operating system, ROS, that is popular now, or it will be an easy implementation in your view from the point of view of programming on those kind of systems. Is that the question, Miguel?
Yes,
yeah.
That's right.
No, that's a very good question. And in the past, I've looked at doing that, like with ROS, and it absolutely is feasible. So we'd have to look at what functions does that system not have. In other words, we use that system for what it has, which is processing the sensor inputs and controlling the actuators. And then what's missing, the part in the middle, the reinforcement learning. So how can we architect that as well as possible? I've looked at that in the past, but I've never done it. Well, now, of course, it's similar in looking at how to implement this in various simulator systems. I've interfaced with about 5 different simulator systems. And so I think it's similar because the simulator provides the sensory input. You have to figure out how to program that connection, and then it has to actuate the things that happen in the simulator, the physical actions. So it's kind of a similar problem. Interfacing,
but
interfacing.
You always develop.
Yeah, go ahead.
The network is trained on a simulator because, and it continues learning when it's implemented in the robot, no? But initially you cannot leave, or there are robots that you can train directly, like through the learning with the physical robot, or usually you have to do a simulation, do the training, because you have to test thousands and thousands of cases, and in a physical robot, unless you have a population of robots and they can communicate their networks between them, like evolving like a human population, it will be difficult. Then you always need a simulator, and then pretty much the same network is the one that you program in the physical robot with the ROS or whatever like platform you have, no?
Yeah, exactly. So you have to make sure your simulator, so we're talking about a 3D physics-based simulator, you have to make sure it's really accurate. And all of them that I've worked with have actually been remarkably accurate. But there was, I remember one case, it was a IBO competitions when the IBOs were really popular. So you had a number of teams that came together. I think it was in Texas, and they actually did that training. They were trying to have the system learn to run as fast as possible. And they actually used the physical robots in real time instead of a simulator. But that's because they had a bunch of people that knew how to program, and they all had their IBOs, and so they all worked together. But of course, you could have done that way faster in a simulator.
But there is an advantage because the simulators for like running and stuff is quite difficult. The mechanics, the simulators are not so precise to simulate all those things that are involved in a dynamic running or marching, or maybe that's an advantage, but then it's costly hardware wise, no?
Yeah, it's surprising how good some of the simulators are. We used one, it was called, various simulators, but we used one that now is not very much in use, called the Obotics. And when we developed simulations of what the snake robot could do in different environments, it predicted better than the humans. We'd run a simulation, we'd say, okay, the robot can make it through that environment, can climb to the highest stair. And the humans would say, no, we've worked hundreds of hours with this robot, it can't do that. And the simulator was usually correct.
So now the simulators are so competitive that you can rely without having parallel robots or things like that. Yeah. Just a final question. The connection between these cognitive networks and the neural networks and the deep neural networks, is there any connection? Because they are like graphical models. They sort of learn through reinforcement, similar to some neural networks. Is there any connection between, and these have like bunch of layers because you do it like, then they are like sort of deep networks, but not necessarily made of neurons or sort of neurons too?
Oh, yes, absolutely. Deep neural network, deep reinforcement learning is simply another more complicated architecture. We had kind of an adaptive deep network back in my earliest work with US Air. So it would actually create intermediate nodes based on a heuristic that I had figured out what were cues that you needed a hidden node, and it would create the node and test it for a while and then decide if it was useful or not. So there are many, those deep reinforcement learning networks are absolutely applicable. They're more computation intensive, but our hardware is much better now than it used to be. So yeah.
And you were able to train because you use heuristics to reduce the space, because the problem with deep neural networks was the no convergence of backpropagation or things like that. But because this is conceptual, you only introduce a node that has a meaning particularly, then the training was convergent, the reinforced training, no?
Yes. If you look at the function of a hidden node, of an intermediate layer, it's to implement an interactive effect. So you have two stimuli that work together. You look at the visual systems, they build up from very low level visual cues to very high level visual cues, and finally into objects. So each layer kind of combines smaller units. That's what the hidden layers are. That's the function of hidden layers. So you can use a simple linear network for a lot of applications, but for a lot of them, you need the hidden layers, which then you're talking about deep reinforcement learning.
Okay, we went over a little bit over the hour. Thank you very much. Let's thank William for this wonderful talk, and we hope to have you in Colombia sometime in the future. Thank you.
Thank you. It'll be a pleasure. Thank you.
Thank you, William. Bueno.
Juan Carlos, ¿paró la grabación ahora sí?
Sí, sí,
quedó
paró
grabando.
la grabación, sí, esperé.
Ah,